All right, so we are going to get started with the last unit or last lesson on Unit 3, which is designing with forces, specifically looking at how different forces might impact a design. So our objectives here are to understand how forces and Newton's laws work together to help solve real-world problems. And we're also going to evaluate some solutions that deal with real world problems in how we look at motion, forces, and collisions. And then we are also going to look at how we can describe forces that act on an object using a tool called a free body diagram. In fact, we'll do that first. So we've got our key terms here: free body diagram, normal force, and tension force. These are our three science terms, and then we've got 4 engineering terms that are going to come into play. So in our first video here, we're going to talk about free body diagrams and also maybe look at some examples of how to draw free body diagrams. So a free body diagram is a way to describe all the forces that act on an object. So we're going to use this as a representation of our object, with our forces being represented as arrows. And we've seen some of these in our study of forces and Newton's laws already, but we haven't really spent much time drawing them. So remember, forces are vectors, and as vectors, they require both a size, which is our numerical value, we call that the magnitude, and we represent the direction of the force. And we're going to use that by giving the forces or representing the forces as arrows. So the arrow is going to indicate the direction of the force, and the magnitude of the force is going to be represented in one of 2 ways. We can represent it graphically using the length of the arrow, or we could just write the numerical value of the magnitude above or near the arrow. Remember, forces are always going to have the unit of newtons. So we need to know some forces, the forces that we have in a free body diagram, the forces that we could see in a free body diagram. We already know about applied forces. These are the forces that you apply when you push or pull on something. So if you are pulling something with a rope, or you are pushing against it with your hands, that would be an applied force. We also have looked at the gravitational force, or the weight of the object. This is the force exerted by the gravitational field on an object. So we're going to represent that with either a W for weight or Fg for gravitational force. Applied force is usually represented as just F, because it's the force that you are intentionally applying on an object, or we could abbreviate it as FAPP for F, applied or applied force. We've also already looked at friction forces. All right, we're going to represent friction forces with a capital F and followed by a lowercase subscript f to represent friction force. It doesn't really matter if it's a sliding friction or kinetic friction, which is another way to say sliding friction, or if it is a static friction or rolling friction. We're going to treat all friction as if it's the same force for the purpose of free body diagrams. And remember, friction is the force that opposes motion, and the strength of that friction is going to be related on the materials that the object and the surface the object is moving against is made out of, because ice sliding against ice is different. The amount of friction there is different from, a person sliding against the concrete, all right, or your shoes sliding against the floor. So the other thing that impacts friction is the weight of the object. So that is also The heavier an object is, the more the friction surface, or more the surfaces are pressed together. The closer the surfaces are pressed together, the more friction is created when they slide against each other. And then we also talked about air resistance, or another word for it is drag force, which is a type of friction that's produced when air is moving against an object. So we're going to represent that as FAR. You could also represent it as FF for F friction, or it can be represented as FD or just a capital D for drag. But there are some forces that were alluded to in our previous studies of Newton's law that we didn't actually define. So I want to spend a little bit now just defining these three forces. All right, and all of them, or all three forces, two of the forces that we're going to talk about are examples of the third force. All right, so we've got normal force, and I've mentioned that before, where normal force, if we have a surface like a table, and we put something on that surface, on the table, that table is providing a force working upwards to keep that object that is sitting on the table from falling through the table to the ground. All right, so that normal force is provided by the table when we put something on the table. So this is what makes a normal force a type of reaction force, because the normal force, which is acting straight up from the surface of the table, perpendicular to that surface, that only is going to occur when an object is sitting on that surface or pressing against that surface. So you sit down in a chair and your weight is pressing against the chair. So the chair provides a force on you. Remember Newton's third law, you're pushing against the chair has to push against you. And the force that the chair pushes against you with is what we call normal force, as long as we're talking about it perpendicular to the surface. So we're going to represent normal force with a capital N, or often it's represented as force normal, or F, with a subscript N. And it has the potential to exist in any surface, but until an object is pressing against that surface, that potential isn't being realized, so it's not there. So normal force is never an action force, like the applied force is an action force, or gravitational force is an action force. Normal force is a reaction force because it's going to respond to an action force. Another reaction force is the tension force, so the force of tension. And this is going to be the force that is being used to stretch a string or a rope that is resulting from the weight of an object or from a push or a pull. So let's say I have a sign I am going to hang from the ceiling, then I would have a string attached to the ceiling, and the weight of my sign attached to the string is going to be transmitted through that string into the ceiling because of the tension force. So the tension force is what's directly impacting the sign, but that's just a way of taking the weight of the sign and transmitting it to the ceiling. The string has the potential to experience tension, but as long as that string does not have a weight on it or is not experiencing a push or a pull, there is no tension in the string. Now we're going to represent tension as a capital T for tension, or a capital F with a subscript capital T for force of tension. And then we have other forces as well that can behave as a reaction force. So we can have a generic reaction force. Normal force and tension force are two examples of reaction forces, but we can have other types of reaction forces, such as the forces that support a bridge would be considered reaction forces. All right, so a reaction force is any force that can only respond to the presence of an action force. So if I have a force acting on an object, then a reaction force would be from that force, would be from that object reacting to that action force, and it is applying an additional force on the object. So generic reaction forces, we can use a capital R to represent them or an FR. Now, we're not going to see this much in this class, but I just wanted you to know that there are more reaction forces than just normal and tension forces. All right, so in the next video, we're going to look at some examples of these forces and how we use them in free body diagrams. All right, let's get to that.